like your evening, your whole life and your day. Every single episode is nothing but dismay. So look away, look away, look away.
Hey everybody, this was a theme song to a series of unfortunate events TV show from Netflix, one of our family's favorite shows to watch as a family, and I played that one just because we're going to get into chapter 8 here, which is sequences and series. So we'll be talking about series in each one of these. So we'll look at what a sequence and series are. We're doing different things a little bit through these. We're doing about 4 different sections here. We're going to kind of just introduce the sequences and series in 8.1 for the most part, and then get more specific with arithmetic, geometric, and then infinite geometric really on the last one on 8.4. All right, so let's get into 8.1 here, which is just defining and using sequences and series. This is a little bit of, like I said, an introduction. We're going to be looking at sequence notation, writing terms of sequences down, writing rules. In fact, a rule would be an equation. So a rule, again, is just an equation where we would write a rule of a sequence. And we are going to find some of the sums of the terms of a sequence and look at what summation notation is. But first, let's do a little cartoon here, a Far Side cartoon. How birds see the world. Nice big bullseyes on top of everybody's heads and top of the dog's back. All right, love that one. Go ahead let's go on to the core concept now next. Okay, so our core concept on page 218, there is a couple vocabulary words to copy down on the top. First of all, what a sequence is, and you can write this down there for your vocabulary. It's just an ordered list of numbers. That's all it really is. An ordered list of numbers. And we're going to have 2 types of sequences. As you can see down below here, we have a finite sequence and an infinite sequence. And then we also have 2 parts to the sequence as well, kind of the domain part and the range part. And remember, the domain and the range are just your x values and your y values. So we have the domain would be actually the numbers here of the the actual term numbers, we would call them. So like term 1, term 2, term 3, a system, like this finite sequence down here, 2, 4, 6, 8. There's a sequence of numbers, a list, an ordered list of numbers, but really this is the first number. 2 is the first one, 4 is the second one, 6 is the third, 8 is the fourth, and that's what we're talking about here, 1, 2, 3, 4, just the number that it sits in the sequence. That's our domain, 1, 2, 3, 4, and the range would actually be the numbers. So we got to think of that as the numbers. So it says the values in the range are called the terms of the sequence. So these would be our terms of the sequence right here, and then the relative position of each term. So this is the first term, second term, third term, and so on. A lot of times they also notate it like this: a of 1, a of 2, where a is the variable, but a of 1 would be like what the y would equal. So you got to remember that the domain here would be like your x values, and the range would be your y values, or we could think of it again as input for the domain and output for the range. Like these are the numbers we're going to plug into our rules eventually when we see the rules. And here, as you can see them down here, like here's a rule 2n. That's an equation. We're going to put these numbers in 1, 2, 3, 4 numbers in there to get and generate these numbers here. So we have the 2 different types. We have a finite sequence, which is just in a finite sequence, a function that has a limited number of terms. So a finite sequence, it stops. Okay, it's got a stopping number. It's going to stop here at the 4th term. It's not going to go any further. But then we also have an infinite sequence, and that's a function that just continues without stopping, and whose domain is the set of all positive integers, so 1 all the way through positive infinity. So this one just keeps on going, and you can see it's got the 3 dots there showing you that it's going to be infinite. So they kind of look the same, but this one doesn't have the 3 dots, and this one does. That tells you it's an infinite sequence, and it's going to keep going. Okay, so for our first 2 problems on the extra practice, we go to page 220. You'll turn the page over. We're going to write the first 6 terms of the sequence, and here's what we call the rule. This is our rule for the sequence. So we got to realize, okay, we have n in this, our n is going to be our relative number of the terms. So first term, second term, third term. We're just going to plug 1 in and plug 2 in and plug 3 in, get the first 6. So 1 through 6 are really your numbers. It's kind of like doing a little table of values as well, as we've done those before. So we're going to choose, like for the x values, 1 through 6, plug those in, find the y values. So first of all, let's plug in 1. So this is going to be a of 1. I'm going to do it just the way it says it here, a of 1. So our first term, 1 to the third power minus 1. 1 to the third power is 1, and 1 minus 1 would be 0. So our first one there is 0. And then we plug in 2. So a of 2. And so this is now going to be 2 to the third power minus 1. And so it's going to be 2 to the third power is going to be 8, and 8 minus 1 would be 7. And then the third one, a to the third, or a of 3. We're going to see 3 to the third minus 1. And now 3 to the third is 27, and 27 minus 1 will be 26. And then a of 4. It's now our fourth term, 4 to the third power minus 1. 4 to the third power, 4 times itself, 4 times, or 3 times is 64. So 64 minus 1 is going to be 63. So as we can see, we can kind of get the idea of what's going on here as far as even just what the pattern of this is. There's always typically some kind of a pattern going on, and that's what we're doing here is we're going to basically cube our term, our relative term number, cube the number for like x in this one, and then just subtract 1. So we know our cube numbers. We see them on our pink chart in class, and 1 to the third is 1, 2 to the third is 8, 27, 64. The next one would be 125, and we would subtract 1 from it. So our fifth one is 5 to the third, so 125 minus 1, which is 124. 6 to the third is 216, so our sixth one will be 216 then, with 6 to the third, minus 1, and that's going to be 215 then. When we come over to number 2, we'll do the same thing. It's just a different notation here. More of a function notation, where this is kind of more in a sequence notation. A lot of times they use this for sequence notation. This is more of a function notation. Just different fancy ways of saying y. Remember, this just means y. Y equals. This is like x to the third minus 1. Same thing as when we've seen before. This is like y, and this is like x minus 1 up here. It's like an exponential, in fact, on this one. So we're going to plug in 1 first, and again it's just going to be 1 through 6, so start with 1, f of 1, so now it's going to be negative 2, and then 1 minus 1 is the exponent, that would be 0. Anything to the 0 power is going to be 1, so our first term would be 1. So it's like if x is 1, then y is 1. There's your like table of values. We can get ordered pairs out of these if we wanted to. Go on to 2, so f of 2, so it's going to be negative 2. 2 minus 1 is going to be the exponent. So 2 minus 1 is 1, and anything to the first power is whatever the base is, so that's just going to be negative 2 then. And then number 3, so 3 minus 1 is the exponent now, so that's going to be 2. Negative 2 squared is going to be positive 4. Notice that our signs are alternating here as we go through. The fourth one, so it's going to be now 4 minus 1 for the exponent on that negative 2. With negative 2 to the third power is going to be a negative 8. So 3 negatives would make a negative there. And then the fifth one, we can kind of see the pattern as we're going through. Basically, we're going to be, kind of cubing or squaring the numbers in some sense, or cubing them in this way. So we're going to do some kind of an exponent to the 2. So it's always going to be done in negative 2. But it's actually 1 less than what our number is. So 1 less than 0, that's why we're subtracting 1 from that. So negative 2 to the 0, this is negative 2 to the first, second, third, this will be negative 2 to the fourth one on this one, which will be a 16. So you just kind of keep doing that to negative 2. You just get a new exponent for negative 2 every time. And so it's going to be just positive 16. And then negative 2 to the fifth power will be next. And so it's going to be, because 6 minus 1 is 5. And so that's going to be a negative 32. Negative because there's an odd number of negatives. Negative 2 to the fifth. Alright, so that's just you're getting the sequence numbers down. That's all it said. Write the first 6 terms of the sequence. So there we got them right there. Okay, so we're going to get into writing rules for sequences, and this can be kind of like the hardest part, I suppose, of this lesson, is actually writing the rules ourselves. And it says when the terms of a sequence have recognizable pattern, you may be able to write a rule for the nth term of the sequence. So it gives you a couple here. Let's just watch these two. So here's our pattern, or our sequence anyways, for A, -1, -8, -27, -64. And for this one we can see, well, these are all cube numbers, perfect cube numbers. So it's like we're going to be cubing the kind of the negative form of each of our numbers as we plug them in. 1, 2, 3, 4, as we plug those numbers in, we're going to be kind of cubing the negative form of that. And so it does say on this one, it says, I think, write the rule. So try to write the next term. So the next one will be the fifth number in the sequence, which in this case would be -5 to the third, -125. The rule would be to take that number, that 1, 2, 3, 4, as we plug in those numbers, make it negative and then cube it. That would be our rule then for that. For the next one, 0, 2, 6, and 12. On this one, like I said, this is the hardest part to kind of understand this and try to see this. But you have 0, 2, 6, and 12. Well, you can think of, we're multiplying here. Basically, you're going to multiply the term number, or the number, like 1, 2, 3, 4, times the number before it. So like 1, the number before 1 is 0. So 0 times 1. And then you go to 2. Well, the number before that would be 1. So 2 times 1 is 2. And then you go to the third one. Number before that's 2, so 2 times 3, and so on. So on the fifth one, we're going to be doing the number before it, 4. 4 times 5 is 20. So there's our fifth term. So here's our rule. We're just going to multiply our number by the number before it, n minus 1. And so you take 1 away from that number and multiply it by the number you have. Okay, so 3 and 4 on the extra practice now. We're going to describe the pattern, write the next term, write a rule for the nth term of the sequence. So it says describe the pattern, so we can kind of figure that one out just by looking at these numbers. But first of all, let's realize we have the numbers 1, 2, 3, 4. We have 4 terms given to us. So remember, this is term 1, 2, 3, and 4. It's good to see these numbers here. And kind of as we're trying to think about how to write a rule for this, because that's a really important thing, is we want to figure out what do we need to do to these numbers up here, like the 1, the 2, the 3, and the 4, to be able to get these numbers down here. So we need to do the same thing to this to get to here. And sometimes it's very simple, sometimes it's not as simple. Like we could say, well, from 1 to get to -3, I mean, I could just, subtract 4 from that. So does that work with this one, right here? If I say, if I just subtract 4, do I get -1? And I don't. So it's more than just that. So you have to really kind of think this through. Do something here where you can do the same thing to 2 and get the -1, and the same thing to 3 and get the +1. So that's what I wrote down over here. What do I need to do to each term number to get each number in the sequence? So each of these term numbers up here, 1, 2, 3, 4, what do I need to do to each of those to get each of these numbers that are in the sequence? As far as describing this pattern, we can see -3, -1, 1, 3. We are adding 2 every time. So that could be describing the pattern. We can describe the pattern just by saying adding 2 every time. And now, what are we going to be doing here to each of these to get this? And so you kind of have to think it through. We could have said, okay, just subtract that, but we could also do more. If we're going to add 2 every time, that really does mean we're going to need to multiply by 2. So this is we're going to see this really come up in 8.2 with a kind of sequence that's like this, where if you're adding by 2 every time, you really need to multiply your variable, your x or your n, whatever, by 2, which would be these numbers. So you need to multiply these numbers by 2. If I multiply 2, or 1 by 2, I get 2. And then now to get back to -3, I would subtract 5. So that could be one option here. So I could do this. I can say my 1 is now multiplied by 2, and if I subtract 5, I do get back to this number -3. Can I do that same thing and get to -1? So if I say, okay, multiply the 2 by 2 and then subtract 5. That's what I'm going to do. Multiply 2 by 2 and subtract 5. So that's 4 minus 5. That does give me -1, which is right there. Can I do the same thing again and get the 1? So now I'm going to take 3, multiply it by 2, and subtract 5. So my pattern is multiplying by 2 and subtracting 5. to each of these numbers. So that's 6 minus 5, give me positive 1. Yes, I got that right. And then do the same thing, 4 times 2, and then minus 5. It's 8 minus 5, which gives me positive 3. So there's what we're doing. Here's what we're doing to each of these numbers to get each of these numbers. And so now we have to kind of just think that through as far as how do we get the next term? So it says, write the next term? Well, we're going to do it with 5 now. So 5 times 2 minus 5, we can do that. So we can just do this. Our fifth term, a of 5, is 5 times 2 minus 5. That's going to give us 5. And we can kind of see we knew the next term because we were just adding 2 every time. If I add 2 to 3, that should be easy to see. But now writing this rule, how do we write the rule? So now we want to say a of n equals. So a of n is equal to, we're just going to now put an n inside here, this parenthesis, where this is. So 2 times n, or n times 2, or 2n minus 5. And that's what it is. So there's our rule. Basically, a rule is like an equation. You're writing out an equation. In this sense, it's very similar to a linear equation, a y equals mx plus b equation. Okay, number 4, we have 5 on the bottom of each of these. We might want to think of this as 1, 2, 3, 4. What are we going to do to each of these to get these? We really don't have to worry about the denominators because they're all the same numbers. We just got to figure out these on top here. So what are we doing to 1 to get a 2? Well, you can just say, well, multiply by 2. Okay. Can I do the same thing here? If I just multiply 2 by 2, do I get 4? Yes, 3 times 2. And so that works. Just multiply by 2 is all we're really doing here on the numerators. So basically you take that first one, times it by 2, and now you have 2/5, which is what we have here. And do the same thing. 2 times 2 is now 4/5, which is what we have. And then 2 times 3, 6/5. And then 2 times 4, 8/5, just putting the 5 on the bottom of each of these. So now we can think, okay, our fifth term would then be to do 2 times 5. 2 times 5 would be 10/5. And so 10/5, we could actually reduce that, though, and we would want to reduce this. I mean, we don't have to, I suppose, but we might need to for the answer. That could be just 2. So we could say we're probably going to say 2 is our fifth term then. These don't really reduce, 2/5, 4/5, 6/5, 8/5. Those can just all stay improper, but 10/5 can reduce to a 2. And so what's our rule? Well, you just exchange these numbers here, the 1, the 2, the 3 that are in the parentheses, with the letter n. So 2n over a 5 is our rule. So a of n equals 2n over 5. There's our rule. Okay, so back page on 218 and 219, back where the vocabulary is, there's some more to add into that vocabulary. We're going to look at what's called a series now. So now a series, what that is, it says, and you want to write this down for series, it's when the terms of a sequence are added together. So we have a finite series, an infinite series. Again, just like we have the 2 different types of sequences, we have the 2 different types of series as well. So a finite series, it has a stopping number. If there's going to be just 4 numbers in that series, it stops at that number. If it's an infinite series, we'll have those dots again there showing could keep on going. So as far as a finite series, we could add these numbers up and find the sum of those series, because that's what it is. Here it says when the terms of the sequence are added together. That's why you see the plus signs now. It's not just commas. There's plus signs in between these, plus or minus signs you might see as well, which means we can add them or put them together. An infinite series, we can't really put these together very well on an infinite series because that would just keep on getting bigger and bigger, but you can always find the sum of a finite series. Now the next thing you want to write there is the summation notation here, and also sigma notation. These two are the same thing. In fact, that's why it says right down here, summation notation is also called sigma notation. So you don't need to write a different definition for each of these. I'll show you what I want you to write for that next to those. But on these series here, we have, this is what that notation is. That's this right here, and this is the Greek letter sigma, and it just means sum. So you want to write that down, that means sum. You're going to now take the sum of this, add them together, find the sum of the series. Then there's 3 parts to this here as well. So we have the number on top, bottom, and then out in front of this, or behind it, we might think of this sigma. So what we have here, what's on the bottom here, this I equals 1. Now I don't like necessarily to use the letter I because that reminds me too much of an imaginary number, and they're using it kind of more like x here. You might want to just think of this as x instead on this one and not think of it as an I. But basically the bottom is your starting number. So we're going to start with 1, which means like as we count through 1, 2, 3, what's the first term in this series? We're going to start with 1. Because we might want to start with 2. Maybe you want to just take the sum of 2 through 4, or something like that. So you could see maybe 2 starting number down here. This number 4 at the top would be your stopping number. So you're going to stop at the 4th term. So we're going to start at the 1st term and stop at the 4th one. So 1, 2, 3, 4. 4 numbers we're going to be adding together. And then this 2i, again, like I said, you might want to think of it as 2x. That is your rule right there. That's the rule. That's where you'd put these numbers in. So 1 would go in for this variable. 2 times 1, then 2 times 2, then 2 times 3, and so on. That's how we get these numbers up here, in fact. So what I would want you to actually write in the vocabulary section would just be probably this right here, where you have this big sigma right there. The top of it is our upper limit. Our upper limit is our stopping number, where we're going to stop. Our lower limit, which is the starting number. Okay, lower limit, we call it lower limit down here. It's the starting number. And then out in front of here is our rule. That rule could be a whole bunch of different types of rules, but that's the rule. It's where we plug our numbers in from our like 1, 2, 3, 4 numbers as we go through. Okay, so back on page 220 on your extra practice number 5, it just says write the series using summation notation. So the first thing I recognize as we look at this series is that it has the 3 dots here at the end telling me that it's an infinite series. So we're going to be looking at an infinite series for this one. And then let's put down our numbers here. So this would be like our first term, second, third, and so on. So we want to maybe write those numbers up on top again just to see. So 1, 2, 3, 4, 5. We have 5 numbers. First, second, third, fourth, fifth. And see, what are we doing here? So we still have to figure out how to write a rule for this. We're going to need to write a rule for the summation notation. So it's just like those last 2 we were writing rules as well. So what do we do to this 1 to get a negative 1? And you might think, well, you can just multiply by negative 1. But is that true for this one? And it's not. So I can't just multiply 2 by negative 1 to get 4. So you have to figure out what you need to do to each of these numbers, and you have to do the same exact thing to generate the term right below it here. And so we can think about, well, look at these numbers, 1, 4, 9, 16, 25. Those look familiar. They are perfect square numbers. So I would be squaring, like 1 squared is 1, 2 squared is 4, 3 squared is 9. So far that works as far as getting the numbers, but then what about the signs? They are changing every time. So I can't just square them because 1 squared is positive 1, not negative 1. So basically what I'm going to have to do then is maybe what if I just do this? If I square it, then I multiply it by negative 1. That would get me this one. But would it work here? If I square it and then multiply by negative 1, no, it doesn't. That would mean that would be negative 4. So I got to think a little bit more deeper in this, where what I'm going to have to do here is I'm going to have a negative 1 times each of these numbers here. So a negative 1 to the first, kind of the first power, would still be negative 1. So now it means I'm multiplying by negative 1. But negative 1 squared would actually change to a positive 1, and now my term will be positive. Negative 1 to the third power, 3 negatives would make a negative. Negative 4, or negative 1 to the fourth power would be a positive, and negative 1 to the fifth power would be negative. So that's kind of what I'm thinking here. So we're looking at squaring all these numbers, yes, to get our numbers here. That's how to get the numbers. So we do have to do that. So it's going to be like n squared down here. We know we're going to have some kind of n squared here as well. But then we're also going to have negative 1 to the n power like this. Negative 1 to the n power. That way we get the right sign in front of each of these numbers. That way the sign will alternate. When it's an odd power, it'll be negative, but when it's an even power, it'll be positive. That's what we got here. And then we can multiply that times our numbers here with the n squared. Alright, so now we kind of get the idea of what the rule is supposed to be. Let's go ahead and write our summation notation using the sigma Greek letter first. That's the notation we got to use. And then we have to put the upper limit, the lower limit, and the rule on this, and that's all we got to do. Those 3 things. So we can start with the lower limit. We're going to see it's starting with the first term right there. So we're going to say n equals 1. I'm just going to use n for the variable. Sometimes they use I, so don't be alarmed by that. You could even use x equals 1 if you wanted to, but a lot of times they use n in this lesson. The upper limit, since it's an infinite series, we're going to have to use the infinity symbol. That will sideways 8. The infinity symbol, since it's an infinite series. There is no stopping number, so it's going to stop at infinity. So that's what we would say there if it's an infinite series. And then our rule, we're just going to write this now over here next to it. So I'm going to say my -1 to the n, and then times n squared. There's my rule. So that whole thing is the summation notation for this series. Okay, so our joke of the day, here it is. Why was the Energizer Bunny arrested? Well, because he was charged with battery. He was charged with battery. Okay, we're getting close to being done. We're almost there. We just have to find the sum now. Find the sum means we are going to actually add this up. So it's going to give us a summation notation. Here, we're going to have to generate all the numbers. Starting number is 4 on this, which means that's the first number you would plug in for the variable. Now, they used k, so don't be alarmed by the letters they use in here. You can pretty much use any letter they want to. So they'd start with 4, like 4 squared, then plus 3. And the last number they're going to be putting in would be 8. So they're going to use 4, 5, 6, 7, 8. Those 5 numbers are what they're going to be putting in. And then you're going to add the results together. So the sum of those 5 numbers in that series. So this is what they're doing here. They're going to generate all of those. So there's 4, 5, 6, 7, 8 going in for the letter K. They're going to square it and then add 3 to those. And they get these numbers now, 19, 28, 39, 52, and 67. They're just going to add all those numbers up, those 5 numbers, and get the answer is 205. So find the sum of this. The sum is 205. On page 219 is this last core concept. It's just a few formulas for some special series. And we might run into one of these as we go through our lesson. As you go through your assignment, you might run into one of these, and you can just use this. But basically, sum of n terms of 1. So if your rule, basically these are the rules, if it's a special rule. So our special rule would just be 1. If it is just a 1, then the sum is just whatever the n is up here, as long as you have 1 as your starting number down there. Because you think about it, every term would be 1. So you plug in, for your first term, that's 1. For your second term, that's 1. Third term's 1. It's just going to be adding 1s together. So if you have 6 up here, that means 6 would be your answer for the sum. 6 1s added together. If it is just the letter, like in this case they're using I again, or they might have said K or N or something like that. If they did that, then it would be this. It would be this number here. Now they're using n for this number. It would be this number here times that number plus 1 divided by 2. So you could use this little formula to find the sum of that. If it is squared, if your variable is being squared, k squared, n squared, x squared, whatever, it's this number again times the same thing here, that number plus 1 times again 2 times the number plus 1, all divided by 6. This is a little more elaborate formula here to remember. So you can just go through this formula, plug it in, and it might be a little faster. And I'll show you why that might be a little faster when we get to our couple last problems here on the extra practice. Okay, so here's our last 2 on the extra practice, 6 and 7. We're going to just find the sum of each of these summation notations here. And so we can see here's the rule. Our starting number is 2, stopping number is 5. So you might want to write that down. That's where we start. This is where we stop. So the first number that we got to put in is 2. So we're going to plug 2 in first. So 2 over 2 minus 1. And then the next one we're going to plug in is 3. So 3 over 3 minus 1. And I'm going to put a plus symbol in between this. Not a comma this time because we're doing a series. We're going to be adding these all together. And then plus 4 over 4 minus 1. And then our last number is 5. So plus 5 over 5 minus 1. And so now we can just simplify this. So this is going to be 2 minus 1 is going to give me 1 right there. So we're going to see 2 over 1 plus 3 over 2 plus 4 over 3 plus 5 over 4 as we just subtract each of those numbers to simplify these fractions. So now what we need to do is, in order to add these together, just like any adding fraction situation, we need a common denominator between 1, 2, 3, and 4. So what number do all those go into? Well, if you take the bigger number here, the biggest number is 4, and just start counting by 4s. So 4, the next number would be 8. Can 3 go into 8? Well, no. 2 could, but 3 couldn't. So the next number would be 12. Can 3 go into 12? Yes. Can 2 go into 12? Yes. And obviously 1 can go into it. So 12 is the common denominator. So we're going to do that. Make all the denominators now 12. We need to adjust our numerators to make equal fractions here. So in this case, we're multiplying 1 times 12. So 12 times this number here, 2, is 24. So it's going to be basically multiplying what you need to multiply. So what did we multiply 2 by to get 12? It's 6. So 3 times 6, it's going to be 18 on that one. This one would be 3 times 4. So 4 times 4 is 16 on this next one. This would be 4 times 3. So 5 times 3 would be 15 on the last one. And so now we can, just look at all these numbers here. The numerators, just add them up. So 24 plus 18 plus 16 plus a 15. Add that all up. It is equal to 73. So we're at 73 over 12 for our answer. That's the sum. And you can leave it as an improper fraction. Number 7, this one it says I squared. And they're starting with 1. So we're starting with 1, 18. At 18 is our stopping number. So there's 18 numbers here to add together. And so we just keep start with 1 and then 2 and 3 and so on. So we're just going to square the numbers. So basically it's going to look like this. 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared all the way to 18. 9 squared, 10 squared plus 11 squared, a whole bunch of these numbers. 13 squared plus 14 squared plus 15 squared, almost there, plus 17 squared, finally 18 squared. So that's what we're really doing here, and we would need to square all of these numbers and then add them all up. Well, we can do that on the calculator here. It might be a little easier to try just using our calculator and just plug it in. So I could say 1, and here's my squared button, 1 squared plus, and then 2 squared plus, and that does work, right? Because that would be 5. And so I would just keep going now. 3 squared plus 4 squared plus, and I'm 5 squared, and I just gotta keep doing this all the way through. Now we're at 6 squared plus 7 squared, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, almost there, 18 squared. I can put equals now. 1837. So actually that was a little off than what I thought it was going to be. Maybe because I didn't hit plus. Okay, so I redid that on the calculator. I'm not sure what I must have hit something wrong, and that's one reason why this is a little difficult. You have to put it all in just perfectly. 2109 was actually the right answer there. It wasn't that other number I had. I must have hit some button wrong at some point going through this whole thing. So the answer there is 2109. Now with this one, that was a little tedious. So this is one of those that did have that special formula that we could have used. It has the variable squared, so we could have used this formula right here according to that core concept, where it would say n times n plus 1 times 2n plus 1 all divided by 6, and the n would be the 18 number right there. That would be your n. So we could plug that in and see how that would work out. So if I plug in 18, and then 18 plus 1 is 19, 2 times 18 is 36, plus 1 more is 37. So it's these three numbers times each other divided by 6. That might be a little easier to do on the calculator here. So I said, okay, 18 times 19 times 37 equals that number, and then divide that by 6 equals, there's my 2109, and I got the same answer. So this one in particular, you had that special formula. It didn't require us to do all that if we used the special formula. But obviously if we've forgotten that formula, then we can just still do it the long way. As long as you don't make any mistakes as you're plugging in the numbers, you'll get the right answer. Alright, so that concludes our lesson here for 8.1. You want to go on to now doing the assignment on 8.1 and big ideas. And I'll see you back in class.